Do it in purple. Physical science time. We're going to talk about, let's just call this electromagnetic waves. Waves and their, whose? Properties. Waves, yeah. Their. And their properties. Electromagnetic waves and their properties. Let's focus it up on that. There we go. That's not really very good. Can I change the way this is? Nope. Well, those of you watching on YouTube, don't forget to like, comment, subscribe, and hit that bell. But no, in a much more real way, this is supposed to say electromagnetic waves and their properties, but the camera must have gone a little bit jacked up. So, okay, so what is an electromagnetic wave? What does it imply? What are the two? First of all, what does it remind you of that we've talked about before, not very long ago? The electromagnetic force. So one of the four fundamental forces of the universe, which let's review those. The four fundamental forces of the universe. So all of the forces that we know of that have ever been observed, God bless you. Remember, a force is any push or pull compelling an object to change its acceleration. Either slow down or stop or change direction. The only four of those that we're aware of in existence, or I should say, there are millions, myriad of forces that we identify, but all of them can be in some way distilled down to one of these four. And let's list them in order of strongest to weakest. What's the strongest of the four fundamental forces? The strong nuclear force. Next. Yep. So it should be electromagnetic. And that's the one we're going to talk about today. Then the weak nuclear, as someone said. And then the gravitational force, which is the weakest, but if you also remember, what else is, if we go in the reverse order, what is this list telling us? If we go from, the longest range. So gravity is the weakest, but acts over the longest ranges, and the strong nuclear force is the strongest, but it doesn't even act over the range of an entire atom for some of the larger atoms. And technically, everything in the universe is under the force of every other thing in all of these. They're all force fields that permeate, and excitations in them cause different particles. And that's the quantum mechanical model. But if we're really measuring them, the drop-off of things like the strong nuclear force is so steep and immediate that we don't even experience the strong nuclear force on any kind of large scale. In fact, even atoms, it would be immeasurable from not just one atom, but from one molecule to the next, we could probably not even measure the strong nuclear force. It's only between subatomic particles. Whereas gravitation, we do not only measure, but we experience the effects of gravity on the macro scale. Like if you your cat off of a 3-story building, it will fall because of the gravitational force, not because of the strong nuclear force. The strong nuclear force keeps the cat from radiating away instantaneously, but the gravitational force towards the ground faster and faster. So what does the electromagnetic force have to do with any of this? Well, electromagnetic force, one way that we can think about the electromagnetic force is, as I said, the quantum mechanical model, the entire universe is permeated with all of these forces as force fields. Just every single, not just cubic inch, but cubic angstrom, the tiniest little, or cubic Planck length, the tiniest length that can ever be measured. Every single part of the universe is permeated by a field that carries all of these forces. And excitations in that cause things like electrons and photons. But a more common way to represent this, or at least a common way to represent the excitations in this field, is as a wave. So the electromagnetic force we usually diagram as a wave consisting of two parts. Two transverse waves kind of superimposed over each other. And I want you to imagine this three-dimensionally. Here's one, just straight up and down like I drew it. And then another is supposed to be at a right angle, like out from the board like this. So there should be like a 90-degree angle. So we're going to say, so that doesn't look like a 90-degree angle, but it's because I'm drawing at an angle. So this is a right angle. And there's another force field perfectly lining up with this one, but at an angle. A better drawing, not made by an actual moron, is found here in your book. Look, Jaden. He's watching the video. This is being live streamed into Jaden's brain. yeah. We set up some special equipment so that he can always get there. Anyway, am I not doing a good? Stare out the window for a little while. Okay, this is the magnetic force. I'm going to put that kind of in little parentheses here. It's not quite it is carrying the magnetic part of the electromagnetic force, but that's the magnetic field excitations. The crests represent magnetic field excitations, whereas the crests of the purple wave represent what then, probably? If our thing is electromagnetic, and one field is the magnetic field, what's the other one probably? Electric field. And these excitations that carry this wave, one thing kind of spooky about all of this, the quantum mechanical model, is that excitations in a wave, when they manifest in the universe, behave as particles. And so we have this idea that the nature of light is a dual wave nature. It behaves as a wave, but it behaves as a particle. And the particles are excitations of the wave. And those things are related, but they're not the same. And in fact, depending on what kind of math we want to do with the electromagnetic force, we either think about the carriers of light, because that's what we're talking about, the carriers of the electromagnetic force being photons, particles, or electromagnetic waves, which are waves. So it depends on what we're going to do. But the speed of this wave, the speed of an electromagnetic wave in a vacuum, the speed of the electromagnetic wave in a vacuum is always equal to, or I should say approximately equal to, it's really something like, I can't even remember. This just gives us in kilometers per second. I'm going to write it as 300 million meters per second, which we usually write as 3.0 times 10 to the 8th meters per second. And that's approximate. I think it's actually, I wish I had this up ahead of time, because your book doesn't tell it. But this is a good estimate. We call this, I've labeled it V sub vacuum for an electromagnetic wave. We usually just abbreviate this as C. C stands for constant. The speed of light in a vacuum always moves. We just in physics by Vsauce saying that there's no reason that this has to be this way. We can easily imagine another universe where it's 299 billion million meters per second. We can imagine a universe where it's 62 meters per second. There's nothing fundamental about the universe as far as we know that says it has to be this, but it is this. It is always this way, and this is the most fundamental thing about our universe. This is the most fundamental thing. This and love are the two most fundamental things about the universe. Fundamental thing. We had fundamental forces, but all of these are mediated at this speed. All of it depends on this, that this is the speed at which these things go.
You're going to roast me, but what's that?
Fundamental means like it's the foundation. I'm not going to roast you. That's not the kind of thing I roast people for. Colin, the kind of thing I roast people for is when they say, I'm not getting a good education. But the things I don't roast people for is when they ask useful questions for everyone, like what does fundamental mean? Fundamental just means it's like the foundation. It's like the very most basic thing that we can think of for this subject. So I did roast you, but not because of the thing you said. Yes, Peyton.
So why'd you change V to C?
Yeah, so this is a specific velocity. It still is a velocity, but this specific velocity we label C because we use it so much. It has its own abbreviation. Good question. All good questions, mostly good questions. Look here, there's a chart on page 358 right above the thing I just showed you saying what the speed of light is in these different, what? There's vacuum, air, water, glass, diamond. What are those? Different media. Yeah, so remember, electromagnetic waves can travel through a medium. They don't have to. Sound waves have to. But these two, it's 358. They don't have to travel through a medium, but they still can. What do you notice about them? What's the highest speed on here?
Vacuum.
Vacuum. This is the highest speed, not only that light can go, but literally anything in the universe. And when I say anything, it has to be, not only is it only massless particles, like photons. There's no mass. Anything, not only can only things that have no mass move this speed, but everything with no mass has to move this speed. Everything with no mass has to move this speed in a vacuum. So why does it slow down? It's not actually slowing down. Here's the trick. In this room, here's the room. Here's your boy. Sorry, I forgot to draw how fat I am. Here's all your little buddies learning, some of them. Here's the chalkboard. Don't even have necks. This one's shaped like the letter J. Here's the flag that is not actually in this room, is it? It's actually outside. Anyway, in here, there's air. And I'm going to draw the air. Obviously, there are not 9 air particles in the room for us all to share, but I'm drawing them rarefied like this because I'm trying to show you something. The next one on that list is water. So how am I going to draw the particles in a glass of water? air. Yeah, close. Not close together, I wouldn't say, but close together. And then in glass, here's a chunk of glass. It's going to be quite a bit closer together.
I have this question on
Just, oh, good.
I absolutely have.
This is a diamond. This is going to be a cut diamond. And I'm going to just fill this one in. Remember that diamonds have a pattern. They're crystal. And so they have a pattern of particles, which I've done a poor job representing here. I'll do another crosswise one so it kind of looks like a pattern. What happens is that when the electromagnetic rays, orange maybe, come into the room, I'm just going to come on in, it interacts with a particle, and then that particle not quite reflects it, but it absorbs it and then releases it. It absorbs and that, etc. And so each individual time it moves, it's going at this speed, but because it makes such a wonky path because the particles are causing it to be absorbed and released, it ends up that the average speed, V sub average, is slightly less than 300,000. So we're going to put 299,000, million meters per second. And this one's because the particles are a little bit closer together. It stops it more and makes it even more path. And so this one, the average velocity, it becomes 226 million meters per second. Your book says that many thousand kilometers per second because I like it better. And so it takes an even jankier little path here through the glass, which causes it to move slower. So the average velocity there is 200 million meters per second. And in the diamond, it has to interact with every single little thing. And in fact, this is why diamonds are not particularly rare. That's all a conspiracy to make people buy them for their fiancés, so that it's basically they've tricked humanity into thinking they're more rare than they are, so they can be valuable. But they are really interesting. They have beautiful properties. Have you ever seen a diamond? Sometime if you like it, you should have put a ring on it. But sometime look at a diamond. It is beautiful, and the reason it's beautiful, it has what's called fire. In the diamond industry, it's called fire. And when white light shines on it, the light is moving slow enough and bouncing around enough that it has all these. It's better than just sparkles. It's better than your holographic Pokemon card because it changes the wavelength of them. And remember, we see the wavelength of visible light as color. And so it causes, even white light entering it, turns into almost like a rainbow, but I would say better than a rainbow. But it also slows down the light. And in fact, when they cut diamonds, like I've drawn a cut diamond here, they cut them in such a way that these exact angles will cause it to reflect in a certain way that causes the fire of the diamond.
So is it possible to make not like it's like we make vacuums, but I mean like to experience the difference between the air and a vacuum,
Like, do you think, you're asking, is it possible to experience the different speeds of light here?
Yeah.
Well, you can't help it. Yeah, all the light you've ever interacted with is probably going at the speed of light in an air. You've never been in a vacuum. Yeah, well, almost. In fact, I think I might be wrong, I might be thinking of something else, but I think that the most rarefied vacuum, like the most vacuumist vacuum that we know to exist was man-made. Like, we can make a vacuum with fewer particles per cubic meter than outer space.
So what do they do with the leftover diamonds?
Probably sell it. Yeah. In fact, diamonds are so not rare, especially poor quality diamonds, that they use them in like drilling operations or grinding. That you can buy diamond powder to grind things with, because diamond is the hardest naturally occurring mineral. You can buy diamond powder relatively cheaply because they're really not that rare. And so when they shape the diamond, they usually shape them with lasers, as far as I know. But when they shape them, they just wipe that stuff away. So if it's a great big diamond and they're like heaving off big chunks, they might then cut this one and sell that too. But
So those things.
okay, let's move on. So all of this, we know it all has to move at this speed. But what can change about it, according to your bell work and according to the laws of nature? The wavelength and the the speed can't change. Well, I mean the average speed changes because it's going in different parts of matter, but the speed itself, the speed of light in a vacuum is actually fundamental, which means it's basic, it cannot be changed. So, but we know from our bell work that V, or in this case C, equals lambda F. And usually we use the Greek letter nu for frequency when we're talking about this kind of wavelength. They mean the same thing. These are both frequency. But usually, when we're talking about light, we use nu for frequency. So let's memorize this equation. C equals, so C is the speed of light in a vacuum. And not only do we know what it is, but we know what it's always measured as. What is it always measured as? Yeah, this is a unit, but what it always has a set quantity. Not only do we know what and what its unit is, but it's always a set quantity. What is the quantity? Oh, I just told you, and you do have to have it memorized, so you better start now. What's the quantity? What number is it always? 300 million. 300 million what? Meters per second. Lambda is wavelength. How do we measure wavelength? You'll sometimes see it measured. You'll sometimes see it measured in nanometers, especially for light. But that's a derivation of meters. And a nanometer is 10 to the negative 9th meters. But we use meters. We just sometimes abbreviate nanometers because they're such small numbers. And then nu is, I like to make it a little bit curlier than that, frequency measured in, how do we measure frequency in sound or light or anything? Hertz. Hertz. And we'll leave that there for now. Obviously we have to. I don't have a choice. Make sure you're reading your book. We will continue this tomorrow. Bye.